Okay, now we're going to get to the shortcut rules. These limits have probably intimidated you to some degree, or may have anyway. But let's introduce. I'm going to state these shortcut rules. I'm going to introduce them, and I'm going to do it without proof. I'm not going to prove why any of these are true. Just take my word for it that they are. The derivative of any I'm going to derivate with respect to variable x. You can derivate with respect to variable u or whatever, or v as in Veronica. There's a lot of letters, or beta, but I'm just using x. I've been doing this the whole time almost. But d by dx of a constant letter, a number c is just some fixed real number, like the derivative of 5 equals 0. Or the derivative of any real number fixed equals 0. The derivative of a fixed real number times f of x is just c times the derivative of f of x. Again, we're assuming that the derivative of f of x exists in the first place here. And on all these, we're assuming that, okay? The derivative of f of x plus g of x entity, closed in brackets or parentheses, is the derivative of the sum is the sum of the derivatives. The derivative of the difference is the difference of the derivative. And guys, why is this true? It has to do with the limits. It ties into the limits. All these things are true for limits, so it kind of makes sense that they're true for derivatives, and they are. The product of the derivative, now that's a little different. This one is actually, it can be proven, but it's a little more tricky. It's not the derivative of the products. Now, for limits, this breaks away from limits a little bit. This does not analog with limits quite as well. The derivative of the product is not the product of the derivatives. It's more complicated than that, but it's not bad. What you do is you leave g alone and derivate f, and then separately you leave f alone and derivate g, and you add the two. Okay? And it has to do with the properties of limits, but it's not as obvious at all. And the quotient is also not as obvious. Okay? What you do is you do g df. I'm using sort of a, I'm just being lazy. I really mean d by dx of f of x, but let me be lazy. So we do g df. We do g times df minus f times dg over the square of ordinary g. So g of x d by dx of f of x minus f of x d by dx of g of x over g of x entity squared. There's a rhyme for this. G is on the bottom, right? So this is low. F of x is my high term, so I'm going to call it high. High and low. Low d high minus high d low over low squared. Okay, make a rhyme out of it. Low d high minus high d low over low squared. Say it faster. I need to say it faster. Low d high minus high d low over low squared. You didn't pay to hear my singing, did you? But it's a good rhyme. It really, I know I'm coming across a little silly, but it works. Low d high minus high d low over low squared. That's the quotient rule. That's a great way to remember it. Now here's the one there's no rhyme for, but it's even more important, as or more. It's the chain rule, and it's a biggie. The derivative of f of g of x, remember this is f composed g of x. The derivative of f of g of x is d by du of f of u times d by dx of g of x, where u is defined to equal g of x. So now that is probably a little muddy. We treat g of x like one whole brick, and in a way we're doing informally, but you don't want to write it like this though. We're doing d by dg of f of g is what we're doing. But it's bad manners to use g. We need to use a substitute letter u here, okay? And we'll do some examples, and this will bring the chain rule alive. It's hard to grasp this. You can kind of tell what's going on with these others, but the chain rule is a weird guy as far as getting your intuitive mind wrapped around it. Like, if I do d by dx, let's do d by dx of, let's say we don't know what f is, but g of x equals x squared. So d by dx of f of x squared, that will be d by du of f of u times d by dx of x squared, but that's 2x. we can show that that's 2x. Okay, you can do the difference quotient limit, and you'll get 2x here. So what we'll have is we'll have 2x times d by du of f of u, whatever that might be. But anyway, or if g of x was the sine of x, remember the derivative of the sine, we showed that it was the cosine. So if g of x is sine x, then we'd have d by du of f of u times the cosine. Because the derivative of the cosine is, because the derivative of the sine is the cosine. The derivative of the sine is the cosine. Okay, blah. I got tongue-tied there. Okay. So now here's some handy differentiation rules. Without proof, just take my word for it. Well, actually, we have proven some of these. But the derivative of the sine is a cosine. We've proven that. I think we've proven a lot of these, kind of. The derivative by limits. The derivative of the cosine is a negative sine. The derivative of the negative sine is a negative cosine. That follows by the yank out property. You can yank any constant. This is -1, or you can yank it out to the side here. Okay. The derivative of the negative cosine is the sine. Notice if you do 4 derivatives of the sine, you come back where you started. We'll talk more about that later. The derivative of the tan is the secant squared. The derivative of the cot is -1 times cosecant squared. The derivative of the secant is the secant times the tangent, or the secant times the tan. And when I say tangent here, I'm not talking about the tangent line. I'm talking about the trigonometric tangent function. Sorry, I know some words get used twice for different meanings. And the derivative of the cosecant is negative cosecant cot. Okay, and without proof, the derivative of e to the x, where e is Euler's number, is itself e to the x. That is weird. E to the x is the one function that equals its own derivative. That is a strange thing. But we have found a guy that equals his own derivative, e to the x. Now, not far behind, but not quite the same, is, now if we just have some general c here, now if c is positive, yeah, we need c to be positive, and I should have specified that, but if c is positive, then d by dx of c to the x equals, I might write it down later, d by dx of, now remember, c to the x is e to the x ln c by algebra, because this e and ln c cancel and would bring you back to c again. But we want to write it like this, though, because here's what we do by the chain rule. If we let u equal x times ln c, then we get, well, we get d, by the chain rule, we get, this is from the chain rule, d by du of e to the u times d by dx of x ln c. Okay? And now u equals x ln c. Again, guys, this is by the chain rule. This is d by dx of my g of x, or my u. Remember, u and g of x are the same. You can think of, well, c to the x, and then we get e to the x ln c. G of x is x times the constant number ln c. F of x is just, f of u is e to the u. Okay, so this is f composed g, and we get this. And so d by du of e to the u times d by dx of g of x, or d by dx of u if you'd rather think of it that way. And so that's going to be, but d by du of e to the u, we're just doing u instead of x here, guys. U is our variable instead of x. D by du, remember what we just said, that's just e to the u itself by what we set up here. Now d by dx of x ln c, now guys, from what we talked about in times past, like if you do the derivative of 2x, you just get 2, or the derivative of 3x, you get 3. So if you do the derivative of ln c times x, you just get ln c, by what we've shown in times past. Like if you do the derivative of a constant number times x, you'll just get that constant number, and ln c is that constant number here. You can show that pushing limits and all that, but in a minute we'll have a way to deal with that. So we get e to the u ln c, but now I've got to make good on something. I've got to go down here, and I guess I need to skip a space, because this is all going in one place. Now, what is u? You need to replace u back in terms of x. So you replace u with what it is, x times ln c. And so there it is. But remember, you got to replace e to this for what it is. You need to resimplify e ln cx back to c to the x. Okay? So you get c to the x times ln c, where u equals the ln of c, and I need to put c is greater than 0, because we wouldn't want 0 and we would not want a negative either. So there's that. And there's, okay. So that's how you handle something like 2 to the x. So the moral of the story, d by dx of 2 to the x would be 2 to the x times ln 2. But with e to the x, it's just e to the x itself. Think about it. You would get e to the x ln e, but ln e equals 1 from algebra. Okay, and e to the x times 1 is just e to the x. Okay, and now this guy right here, d by dx of x to the r. Now here's a very important rule called the bring down rule. D by dx of x to the r is r times d by dx of x to the r minus 1, where r can be any real that we wish, but x has to be domain appropriate. Sometimes, x could be in all real numbers. Other times, if r is negative and is irrational, we'd have to choose x to be strictly positive. So it just depends. X needs to be domain appropriate. But just remember this rule right here, okay? Okay, what have we done here? This is important. We brought down the r, and then we subtracted 1 off this exponent that's new here. And you know what? Did I mess up? I sure did. No. We don't want d by dx. The whole point is to get rid of d by dx. So sorry. So d by dx of x to the r is r times x to the r. And I don't need these brackets are kind of silly. And now everything is going kind of haywire. So this is just, excuse me for a second. Sorry for the silence. Okay, there we go. Much better. So d by dx of x to the r is rx to the r minus 1. I don't know, I just made a goof there. Now, the next thing, and this is important, so you bring down the r and you subtract 1 off the exponent. Next, d by dx of the ln of x is 1 over x, as long as x is positive. It doesn't make sense if x is not positive. Okay, so the derivative of the ln is 1 over x. Now, what about any log? Notice ln can be thought of as the log e of x. But what if b is not necessarily e? Well, then d by dx of the log b of x will be d by dx of, remember from algebra, the log b is the ln x over ln b. But 1 over ln b is just a constant. You can yank it out, and you get 1 over ln b times d by dx of the ln of x. So that's 1 over ln b times, hey, 1 over x, from what we said just up here. So there's that, but hey, that's just do top times top over bottom times bottom. That's just 1 over x ln b. Okay? Where, of course, it's understood that b is positive, and b is not 1, and x is positive. But anyway, there's that. And I already told you that x is positive, but anyway. Now let me generalize. You remember we brought down the r and then turned the exponent into r minus 1? Now, so here's what we do. We generalize that, and if there's somebody in front, it doesn't matter. Like, what we do is, you know what? I messed up again. If I derivate this, and this is wrong, I need to fix it. The n goes down in front, and we get like here, and now parentheses, n minus 1 goes down in front here, and then that becomes, that's right. And then, let's see. Well, what goes in front here? Now, by the time we get over here, well, that's going to be 2. And then, let's see, a1x, if I derivate, no, wait, that's not 2. That's just a1. Because if I derivate a1x, I just get a1. So what's going on here? I get n a n x to the n minus 1. I decrement the exponent down by 1 and bring the n down. So it's n times the same a sub n. A sub n is just a constant fixed real number. So I get n times a sub n times x to the n minus 1 plus parentheses n minus 1 times a sub n minus 1 x to the n minus 2 plus parentheses n minus 2 a sub n minus 2 x to the n minus 3 plus parentheses, n minus 3, a to the n minus 3, x to the n minus 4, plus so on and so forth. And then you'll eventually get to, well, now, you remember we had a1x1, now a2x2, what would that be if we derivated it? It would turn into 2a2 x to the 1. And that's understood. See this plus dot dot dot? That's my other terms. And all the other dudes, this is understood to be everybody in between here and for this other guy here, okay? So we would have a 2, and we'd have 2a2x to the 1, and then we'd have and then also to the left of that, separated by the plus sign, we would have 3a3 x squared, then a 4 x cubed coming in from the right, okay? But anyway, there's that, and that's going to come in handy, of course. Now, without proof, the derivative of the sinh is the cosh, and the derivative of the cosh is the sinh. Notice that's a little different. With sine and cosine, you get negatives, but you don't get that with these, okay? Now, where the cosh is this guy right here, and the sinh is defined to be this guy right here. This is by definition right here, okay? Now, very differently, the derivative of the arc sine is 1 over radical 1 minus x squared, and that's going to be the negation of the derivative of the arc cosine, by the way. And we're just going to define arc cosine hence to be neg 1 over radical 1 minus x squared, okay? And where x is in this open interval. I don't want to deal with the endpoints. I might talk more later about one-sided differentiability, but I'm trying to shy away from that for now. The derivative of the arc tan is 1 over 1 plus x squared, and which is going to be, and the derivative of the arc cot is just going to be negative 1 over 1 plus x squared, with the negative 1 up here. And then the derivative of the arc secant is going to be this, and the derivative of the arc cosecant would be negative 1 over this denominator. And the derivative of the tanh with a h, excuse me, no, we define the tanh to be this, and we define the sech to be this. We define the cosech to be this and the coth to be this. And guys, to do the derivatives of these, what you can do is just do low d high minus high d low over low squared. And likewise, you can do that here too, okay? And likewise here and here. So I'll leave that as an exercise. Let's do some examples. And the derivative of a constant 7, we already told you it was 0, but let's justify it with other rules. Notice that 7 can be thought of as 7x to the 0, and if I'm going to do it this way, I need to put parentheses around that, because that's in the derivative operator. Okay, and remember, by the rules, you bring the 0 out in front, and then you chop down 1 to negative 1, but none of this matters, because 0 just kills everything, and I get 0. The derivative of any constant is 0. And I'll leave it to you to do these. Guess what the answer is going to be? I'll leave it to you. Okay. The derivative of x is going to be, well, it's 1. And here's why. There's an understood 1 in front here, and there's an understood 1 up here. You just bring down the 1, which doesn't matter. 1 times 1 is 1. And x to the 0 is 1, so it's a big 1 festival, and we get 1. So the derivative of x is 1, the derivative of 2x is 2, the derivative of 3x is 3, the derivative of negative 5x is negative 5, the derivative of pi times x is pi. You get the point. For the same, it's going to be for the same reasons. And the derivative of negative x is negative 1. You get the idea. So there's all that. And I'll leave this one for you to do. Now, I'm about out of time. The derivative of 6x to the 10, that's just you bring out the 6 by the drag out law. You just drag the 6 out. And then by the come down law, the 10 comes down. So it's 6 times 10x to the 9th. But by associativity, you might as well just go ahead and multiply that. When that 10 comes down, just multiply it into that 6 and get 60 by associativity. And you get 60x to the 9th. Now, if you have a negative 6 in front, you'll just get negative 60x to the 9th. And I'll leave it for you to do this one. I'm out of time, guys. I'll see you on the next video.